Welcome back. Today's topic is boundary conditions at dielectric interface. In the last video lecture, we have discussed about polarization concept in dielectrics. We have developed expressions for determining the polarization in dielectrics, and we have come across different terminology which we generally employ in electrical engineering. The concepts called as susceptance, dielectric constants, and absolute permittivity. So all these terms we have come across in the last lecture. Now in today's video lecture, we will discuss about the dielectric interfaces, what happens actually at the interface of dielectric materials. So I hope that you will be able to develop expressions for boundary conditions at dielectric interfaces. These can be employed for determining the fields and flux densities when you encounter dielectric interfaces. Now, let us come back to the topic. Most of the times in electrical engineering, we don't use a single dielectric medium. We do use combinations of dielectric mediums. Let us suppose there is a long copper wire. Let us suppose this is your copper wire, or maybe an aluminum wire. So normally it is a practice that we will cover it with some sort of dielectric material, but there may be an additional coating over this one. You take any underground cable, generally it will be having 3 to 4 layers of dielectric materials bound around it. For each of these dielectric material will be having a specific purpose. So if you take the cross section of this particular material, then you will see that here there will be a conductor, and over here there will be a dielectric 1. Here again you will see a dielectric 2. Again you will see some sort of dielectric 3. So there is a bunch of dielectrics which will be present over a single conductor material when you see a cable. So it is a normal practice that if we don't have the required dielectric material with required properties, then we will use a combination of dielectric materials for a specific application. So the concept of dielectric interface is of more importance when we are in the design sector, because we are employing a combination of two dielectric materials. So this is dielectric 1, and let us suppose this is dielectric 2. So what happens at this interface between these two dielectric materials? This is of utmost importance when we are designing any particular electrical item, because in these two dielectric materials the electric field intensities and the electric flux densities may vary. If it is a single material, then we can utilize all the equations which we do have. Let us suppose if there is a charge here and I want to determine the field here, then automatically what happens? I will directly employ E is equal to Q by 4 pi epsilon R square, right? But let us suppose if it is having a medium, up to here this is one medium. Let us suppose if it is another medium. So how to determine the electric field intensity in this medium too? Then this boundary conditions come into picture. So in today's class we will see what are the boundary conditions, how boundary conditions can be employed to determine the electric field intensity when you encounter a change in the dielectric material. Okay. So for our easy understanding, now let us suppose we consider a simple two dielectric material with different properties, and these two dielectric materials, they may differ in different behaviors. We will assume that the direction of fields, dielectric fields, it will be changing with respect to other media. Let us suppose if it is this medium D1 and this is D2, let us suppose the fields will be in this direction. It may not be the same. The directions may change. It depends upon the property of that particular material. So I am considering two dielectric materials, D1 and D2, and the permittivities of these two materials are epsilon 1 and epsilon 2, which are equal to epsilon naught into epsilon r1. They have discussed this epsilon r. epsilon is called as absolute permittivity, which is a combination of this one, right? This is called as relative permittivity or dielectric constant. So I am taking two materials, so epsilon 1 and epsilon 2, which are these things. Sorry, this is, yeah. And I'll assume that at this particular interface there is no charge on the interface. This is an assumption which I am going to consider, which will help me in developing the equations quickly. So what is the assumption? There is no charge on the interface between the electrodes. And I will apply the Maxwell's two equations which we have developed so far in unit number 1. So what are the two Maxwell's equations? This is the first equation, right? It states that surface integral of normal component of electric flux density vector over a closed surface is equal to the charge enclosed by the surface, isn't it? Which means that let us suppose there is a charge and it is developing electric flux around it. So whatever the flux density which is there normal to this surface is equal to d, which is radial out of this surface, is equal to entire surface is equal to the charge which is enclosed by this one, isn't it? Actually, surface integral of flux density is nothing but electric flux, which is again nothing but charge. This is your first law of Maxwell's, first equation of Maxwell's. Now the second equation states that line integral of electric field intensity vector over a closed loop is always equal to 0. So I'll employ this one. See, this is Maxwell's second equation, right? V is equal to minus integral of E dot dl. This was Maxwell's second equation. I have improvised this one. So which means that if I consider a line from point 1 to point 2, integral of E dot dl or the entire line is nothing but V in opposite direction, right? So if I consider an entire loop like this, so what is the, if I start from here, if I complete it over the closed path, automatically the voltage as per the Kirchhoff's laws, the voltage across a closed loop is always equal to 0. So that's why I am taking it as 0. But the condition is that I am doing it over the entire length, closed path. So this is my second equation which I will be considering today. So employing these two equations, now we will start deriving the boundary conditions. Okay. Now, so this is my boundary interface which I have considered. This is medium 1 and this is medium 2. And in this medium 1, let us suppose the flux density is d1, field intensity is e1, and this is d2 and this is e2. Now let us suppose this is the direction of, both will be having the same direction, isn't it? The relation between these two is, or I can write it as, similarly here it is, right? These are the two equations. Now let us suppose this is a direction of d1 and d1 and this is a normal to the boundary. So the angle here is alpha 1 and this is the angle which is made by d2 and e2. So d2 and e2. This is d1 and e1. The angles made normal to the boundary are alpha 1 and alpha 2. If let it be theta 1 and theta 2. Okay. So this is the scenario which I am considering, that d1 and d1 and d2 and d2 or the flux densities and field intensities in the two mediums with their vectors making angles of alpha 1 and alpha 2 to the normal to the boundary. Now I will start applying these equations one by one. Applying Maxwell's first equation. So to apply Maxwell's first equation, I will consider a small box type thing. This is my surface, right? This is my medium 1, this is my medium 2. So what I will do is nothing but I will consider a very small surface here. This is my small surface which I am considering. Okay. And this surface, let me suppose it is having a concept of ds. Actually, it must be a three-dimensional one, but what I am considering is, I am considering just like a pillbox type of structure. Pillbox type of structure means this distance will be very minimum. Only it will be having just like two surfaces, right? So the surface 1 and surface 2, surface 1 is extending into medium 1, surface 2 is extending to medium 2. So this is surface 1, this is surface 1 extending to medium 1, and surface 2 it is extending to medium 2. And both will be equal. I'll considering this surface as delta S and this is also delta S. And there are no other surfaces. That's why I'm considering it as a small pillbox type structure, a three-dimensional imagination of a minimal volume at the interface of the dielectrics. So this is my three-dimensional one. This surface area is delta S and this is delta S. And I'll assume that the directions of these vectors are D1 and D2. Okay, this is D1 and it might be making an angle of somewhere around D2. So this is alpha 2 and this is alpha 1. Okay, so this is dn1, which is now d1. I am dividing into two components. This is dt1 and this is dn1, and here also I am dividing it into dt2, tangential component and normal component. Okay, so these d1 and d2 are now divided into these two things. Now what is my question is, applying Maxwell's first equation, it states that normal component of electric flux density vector over the closed surface is 0, isn't it? How many surfaces are there? I am considering this surface is 0. So to me, only one surface is in medium 1, another surface is in medium 2. So in medium 1, if you consider what is the surface, this is delta S. Medium 2, it is also delta S, isn't it? So medium 1, delta S is a surface, and what is the normal component of the d1 vector? It is dn1, isn't it? That must plus dn2 into delta S is equal to 0. But literally speaking, both are in opposite directions. So I'll take it as dn1 delta S minus dn2 delta S is equal to 0, isn't it? So this is what I have applied here. If you carefully see, applying Gauss surface, assuming it has only two surfaces, each extending into either of the medium. See, this is Gauss equation, right? So this is for surface 1 for medium 1, and this is for medium 2. Since it is assumed that the charge enclosed is 0, I'll make it as this one as 0, and since the directions are opposite, I'll take it as minus. So this is my equation. So this is nothing but, if I take delta S common and equal to 0, this is my component, which is nothing but dn1 is equal to dn2. So what is actually dn1? d1 dot n1 is nothing but dn1. So I can write it as d1, normal component, right? We have already seen this one. This is another video, right? This was alpha and this was alpha 2, right? So this is E1, this is D1 and this is D2. So I want this component. So what I will take, this is D1 cos alpha 1, right? So that's why D1 cos alpha 1. This is a normal component, dn1. This is also dn2. So D1 cos alpha 1 is equal to D2 cos alpha 2. This is my first expression of boundary conditions. Try to remember this. And coming to second expression, now we will apply Maxwell's second equation. For Maxwell's second equation, what I'll be doing is nothing but I'll be considering a path ABCD. This is my path ABCD. I'll assume that this length is very minimum. I don't consider. So these two lengths are very minimum. I'll consider only these two lengths now. Okay, and the length each one is L and L. So similarly, again, if you carefully consider, what is a vector in this one? Actually, E will be in this fashion, isn't it? E2 will be in this fashion. So what is the vector in this fashion? So it is Et1, tangential component of E1 dot L, because this is the Maxwell's second equation, right? So Et1 dot L plus Et2 dot alpha. On this is in medium 1, this is in medium 2. But if you carefully see, ET1 and ET2 both are in opposite directions, so I'll take it as minus. So this is my expression. So if I take LS common, so this is my expression. So what does it mean? E1 sin alpha 1 is equal to E2 sin alpha. This is my second expression. Now if I employ two expressions now, if I consider these two expressions, this was the first expression which I have obtained, and this is the second expression, dividing 1 and 2. So you know that d1 is already equal to, this is d1 and this is d2, right? So what I'll get, e1 gets cancelled, epsilon get cancelled. So epsilon r1 into cos by sine is cot alpha, here also it is cot alpha. So this is my third expression. So the final expressions are, this is 1, this is 2, and this is 3. So these are the expressions. So how will I employ these expressions? As already I told, let us suppose these are two media, and these are making an angle of alpha 1 and alpha 2, and this is d1 and this is d2. If I know alpha 1 and alpha 2 and d1, so automatically what is d2? d2 is equal to d1 cos alpha 1 by cos alpha. This is the way how I will determine electric flux density in the other medium if d1 is already known. Okay, so I hope that you can employ these boundary conditions. So this was our target and we have reached our target. I hope that everybody has understood now how to develop boundary conditions at interfaces. And your homework is, you should develop boundary conditions between a dielectric and a counter interface. You assume that there is a dielectric here and this is a conductor here. So now you are supposed to apply these three things and determine the boundary conditions. Okay, that's it for my side. Thank you. We'll meet in the next class and we'll start Laplace equations and